In this video, we're going to learn about design for additive manufacture, specifically for a micro drone. Hey everyone, this is Matt with Learn Everything About Design, and in this video, we're going to tackle a project, or at least a portion of a project, that I've already done before. And we're going to give a little background information on that in just a second. But the overall goal is to design a part specifically for 3D printing and understanding some of the limitations, some of the design decisions that we might decide to make in order to make the design fulfill our requirements. So now for the backstory. If you're not interested in this at all, you can go ahead and skip to the next chapter. But there is a competition in the UK called Airgineers. Now, Airgineers has been around for quite a while, and they are rebooting or updating their competition to the best of my knowledge. Now, this is a great competition where you use some off-the-shelf components and you 3D print your own micro drone chassis. And there are some skills that you have to go through. There are some challenges. And overall, it's just a very nice entry-level project for someone to get into drones, to get into micro drone racing, and just design for 3D printing. You can go to the description of the video and you can take a look at the link to the Airgineers, in this case, their website. There's a couple things that I want to talk about here. Now, one, I've already done a course on this for Autodesk several years ago, and unfortunately, that course is no longer online. So I wanted to cover some aspects of this process that's not going to be a full course, but we're going to talk about some of the design decisions that we're going to make and not really do the full project. Now, if you want to go through the full project, there are videos on here on this website. You can go to Rapid Education to purchase the kit, which will include things like the goggles, the cameras, the flight controllers, the motors, the propellers, all of the different pieces you need, with the exception of the chassis. Now, I should state that I have no affiliation with Airgineers. I have done a course for Autodesk for this before, but you purchasing the parts from Rapid Education versus anywhere else does not affect me at all. So don't feel like it's necessary for you to go directly to Rapid to get these. However, if you are planning on doing a competition like this, if you are in the UK, then getting all the components from one place is certainly helpful. And also note that as you go through this website, even though my original course is gone and not online anymore, there are still YouTube videos from the original course that were done by Mark Chester. Now, these videos go through the entire design of the chassis that you see in his renders, and it also goes through things like the assembly of the drone, as well as the programming of the flight controller and the programming or setup of the controller itself. These are aspects that I did cover in my original course, and they will not be covered here. We're specifically going to focus on some of the design decisions in the chassis, things that aren't necessarily covered when you follow along a step-by-step how-to. Now, obviously, if you're going through this competition, you are going to want to make your own unique chassis. So what I'm going to be doing is I am going to be providing some of the initial data set, but I won't be providing the final chassis. I want to make sure that everybody designs their own. And really, we're going to take a look at getting most of the way there and not offer a complete solution. So as we go down, there's also some downloads. You can download the CAD assets directly from this website. And these include the flight controller and the frame, the sample frame that they have, the motors, the battery, the propellers. In the description of my video, you can also download a Fusion 360 file that already has the controller, the motors, the battery, and the propellers in place for where I'm going to design. So you can determine your own size and requirements if you are going through the micro drone program for Airgineers. Just note that they do have rules. There will be a specific bounding box that all of your components need to fit in, and that's going to drive the location of some of these elements. So all of that out of the way, I just wanted to make sure that we understand that this is a full project and there are resources already available on YouTube. If you go to Mark Chester's original videos, you can find information about the controller setup, the flight controller, how to program that, and all sorts of things. We're not going to be covering that. I think I've mentioned it quite a bit, and we are going to be focusing on the design aspect. So with that in mind, what you see on the screen is going to be a sample. We're going to design something similar to this, not exact. Now, I have printed this chassis and flown it, and it does pretty well. And we're going to talk about some of the criteria, the design elements that we need to follow for that. The starting point that you can download is going to be the motors, the propeller, the flight controller, single battery, and a camera. Now, it is important to note if you are going through the Airgineers sort of competition, in order to power the camera, you'll need two batteries or you'll need to modify the wiring so that you can plug the camera and the flight controller into a single battery. Now, there are pros and cons to each of those. The pro with running a single battery is weight. You obviously are quite a bit lighter if you're only running one battery. The downside is flight time, so that's something that you need to play with and balance. Now, I have done an entire drone series before that's on Coursera and I believe Udemy right now. This was a full series that was, I think, in 2017, where we talked about things like the thrust of the motors and propellers and picking all those different design elements out and understanding where you sort of had to be in terms of chassis weight for the performance that you were getting. We're not going to be going that deep into it, but I will give you some basics on some of the ranges that your components should fall into. So with this chassis right now, this is going to be around 7 grams, and it's missing some components still. So when we look at the physical, you can see mass here is 7 grams. The thing that it's missing is a camera mount. Now, you don't necessarily need the camera or 2 batteries to fly this thing. You can fly it with line of sight. But if you do want to use the goggles and you do want to fly it as a first-person experience, then you will need to include those elements. Now, the 7 grams for the chassis right now, again, doesn't include any of the components like the motor, the prop, the controller. Those are all sort of fixed elements. Everybody would have those, and it's not going to matter if your design has something different in those areas because they're all going to be the same across the board. That's part of the reason for the competition. A starting point, everybody has the same equipment. Where you're going to want to focus your attention on is the main chassis, as it's going to be the biggest item in your entire design. Now, when I did this course originally, I found that all of the plastic pieces together around 10 grams was sort of the upper limit. You didn't really want to go past that 10 grams for all of the plastic components that you're using. And the reason for this is that you just don't really have the thrust or the propulsion to make that work. So with that in mind, the main chassis should really be somewhere around 4 to 5 grams. The lighter, the better, obviously. And that's a balance that you're going to have to figure out where you really want to spend time saving weight. Now, what I ended up doing for this original version is I really wanted to focus on using some lightweight techniques, in this case, using some sort of hexagonal structure and very minimal frame around the outside. You can also see that I added some additional components underneath here. These thin pieces were screwed on with the same screws that held down the flight controller and the camera, and they're used to house the battery and prevent the battery from sort of contacting or going into this pocket area. And there are a couple of reasons why I went that route, and we'll talk about that just a little bit. But this is going to be sort of the main workflow that we're going to talk about. With that in mind, there are a handful of general design notes that we should cover as well. After we get through these design notes, then we'll start to get into the CAD section. But if you're watching this video, you're likely interested in understanding some of those design decisions along the way, and having a good foundation for what your end goal is important before you ever start any sketches or features. So the list, when I think about a project like this, the first thing that comes to my mind is what method are we using to print? Now, in this case, I'm using a desktop FDM machine or FFF machine. That is going to be, for me, a Creality Ender 7. And this is a really good machine because it's relatively fast. There are plenty of other machines on the market depending on what you have access to, whether it's an SLA machine or SLS machine if you're at a university and you're ordering your parts. And you can obviously choose whatever process fits your requirements. There are going to be pros and cons to each of these. Now, with the FDM machine, desktop machines, you have a whole host of material choices. I'm going to be using a PLA, and one of the reasons I like to use the PLA material is it has really high quality on the final print. It's not really going to survive the test of time, and it's not really heat stable or moisture stable, but there is a level of the ability to biodegrade these PLA materials depending on what you have. So that for me is a big benefit, especially if I'm going to be doing multiple prints to try to fix or finalize the design. I might do a lot of that in a material that is more environmentally friendly, like PLA. Now, obviously, if you're using like an SLA machine, you have a lot of material that you need in the resin, and then you also have cleaning material, and there's all sorts of implications to using those types of printers and materials for your final parts. So I'm going to be focusing on, again, FDM using a PLA material. Now, obviously, if you have a pretty solid final design, you want to use something like a PETG or an ABS-like material, then you will have to think about the speed at which you can print as well as the quality of the final parts. And the reason for that is because we have small holes on this part. We have a somewhat press fit for the motors, and these are all criteria that we need to think about. The next thing that I begin thinking about after I've chosen the printing method and I've chosen my material is going to be the geometry. Now, the geometry in this case, if we take a look at it, the reason I have included this extra piece on the bottom for the battery and this extra piece here to hold the batteries in, the reason I've done that is because I want the entire bottom portion of my chassis to be flat. Now, the reason I want it to be flat is because I want to print it completely flat on the build area without any supports or raft or anything that I have to clean off afterwards. With that in mind, everything here that you see can be printed unsupported. There is one slight exception to that rule, and that's the little lip at the top. That is going to be the stop for the motor. Now, we can get around that because the top of the motors aren't completely flat. They do have a little bit of a radius to them. So you can put a small lip on the top and a very small chamfer on the inside and help with that unsupported nature. You obviously wouldn't want to make this diameter very small because then you have this huge unsupported area. And if you have support material building in that area that you have to clean out, it's going to be a mess. Now, some printers are better at the support material than others, but I've just found in general that these FDM machines, if you can get away without support material at all, your final design will be much better off. And that's simply just because you don't have to sit there and post-process it. So that is a reason why we have these extra little pieces. Another reason here is that these can be printed relatively thin. They're not structural in nature. This is going to be holding the batteries, and this is really just a block plate. So this can be relatively thin. It doesn't have to be printed very thick. And if we take a look at this, you can see that if I look at this in millimeters, so right now we've got secondary units in inches, 1 millimeter thick, 0.039 inches. That is a really thin part, and it works just fine in practice. I'm running the screws all the way down through all of these. I do have nuts that I could put on the backside. I have found that I don't really need them as long as I drill these holes out the right size. So, those design elements of understanding the limitations of the printer, whether or not you're going to be designing for support material, and things like what the overall unsupported angle your machine can print is. Now, with the Creality that I'm using, it's 49 degrees. I can go up to 49 degrees and it will do just fine. Anything above that, you start to run the risk of getting these strings in the air from trying to print on this unsupported area. Sometimes it'll work okay depending on the orientation of the slicer. Sometimes it won't, and it's kind of just something that you have to think about. So we're going to be going forward looking at building something without support materials at all, and that's going to influence our design decisions as we go through. So another thing that we also need to think about is going to be test prints. And what I mean by this is that if you print a 6 millimeter diameter boss, is it actually 6 millimeters when it comes off the printer? Now, you'll find that depending on the material you're using, depending on the printer itself, depending on its resolution, the resolution of the STL file that you output, all of these different factors are going to come into play when you talk about the size of those features. Now, in this instance, I have done a couple test prints to figure out what size I need to print to get a good press fit on the motor. You don't want it to be too tight, but you also don't want it to be too loose that you have to glue the motors in. These motors are small and they tend to burn out after a certain amount of time, so you want to be able to replace them if needed. So what I found is through some testing that if I design a boss at 6 millimeters, it actually prints out at 5.7 millimeters, give or take. Now that means that is the 6 millimeter motor is not going to press into that. It's just too far off. So I need to up my size by about 0.3 millimeters. So if I print 6.3 millimeters, I end up with about a 6mm boss so I can press the motor into it. This is something that you need to figure out when you're doing your design, is to really understand what the resolution, the final output of your part is going to be. So now that we have all of that out of the way, I'm going to move over to the starting point. This is the data set that you can download, and we're going to talk about how I would start a design like this. So first of all, the camera, I don't really need to see it. It's not going to be a big part of this. The flight controller is important, and some of the reasons for that is because we need to make sure that our chassis design doesn't go over these connectors. We need to go around the outside of those connectors. The propellers are going to be somewhat fixed, and the reason that they're where they are, again, is based on a bounding box for the competition. Everything needs to fit within that, including the camera, not the antenna on top, but there are requirements that you need to follow if you're going to be using sort of the Airgineers format. Now, I think it's good sort of as a practice to have an end goal and some design constraints. Otherwise, you can just go down in this sort of endless design iteration. You need to have an end goal in mind, and the end goal for us is going to be a chassis, and we're going to shoot for around 4 grams with an ABS material. What I found that is also important when you are printing, depending on what printer you're using and what slicer, is when you slice the part, oftentimes it'll tell you how much material is being used, and you can kind of correlate that to the mass properties in Fusion or whatever CAD file you're using to see how closely those are. So if I say that my chassis is 4 grams and I take it to the slicer and it's telling me it's 6 or 7 grams, that's obviously a very big difference, and we need to understand and account for that. So with that all out of the way, let's go ahead and get started on the design. Once again, you can download each of these pieces individually from the Airgineers link in the website in the description. And you can also download this data set as a starting point if you want to use the exact requirements that I'm starting with. So when we think about a design, there are many different ways that we can go about the overall process of design. We need to think about if we want propeller guards and how much we want to build out. If we take a look back at the Airgineers site and we take a look back at the original design, you can see the original design goes completely around the propellers. It's offering up an entire guard for those propellers. You can see that the design that I did actually went a little bit further with that concept and made some cones to help funnel the air and get more lift. Now, ultimately, that's a lot of weight that you have to add. So these are all design decisions, and if you want to go the route of building an entire shroud for the propellers, then there are other aspects of the design that are going to be problematic. Things like the camera view, the overall mass, and all of the components there. So all these are important considerations that you need to think about when you're getting started. For me, when I want to start a new design like this, I think about symmetry. Now, this entire design is based around the origin. If we turn the origin on, it's right in the center of the controller, and everything is going to be able to be patterned. So we can just work in one quadrant, and I like to focus on the upper right-hand quadrant. This is typically quadrant 1 or the positive quadrant if you're thinking about a coordinate system in math. So I like to focus on that, which is going to be X and Y positive in general. Now, it depends on the orientation of your design. This is built in the Y up orientation, so really it's looking at positive X and negative Z. Doesn't really matter because as soon as we make our sketch, we're just dealing with X and Y. So I want to focus on that upper quadrant. So none of this stuff really matters to me. I'm going to leave it visible for now, but it really is just going to be a pattern. And then what I want to do is I want to think about how I want to ground or start my design. Now, the main aspects of this design are going to be the top of the motor. So the top of the motor here is going to be sort of a fixed position, and the bottom of these spacers for the flight controller. So those two areas need to be connected, and everything else is just going to be extra. So really, I want to build from the top of the motor down to the bottom of that spacer, and that's going to be my starting point for my design. So I'm going to select the top of the motor, right-click, and create a sketch. Now, when we start the sketch, I want to start projecting some elements. First, I want to get rid of the propeller for right now. I'm going to bring it back, and I'm going to use Create, Project, Include, and P on the keyboard, or select Project here. Now, what I want is going to be the outside of the motor and the outside of each of these bosses. And remember, we're working in this quadrant, so we're going to be connecting these together. The other thing that we need to think about, again, is going to be obstructions on the flight controller itself. There are connectors underneath that need to go down past the battery, and if we build too much underneath the board, then we're going to have problems. So what I want to do is I want to think about the sizes that I need, and I'm going to use the circle tool to get started. So from the center here, I'm just going to draw a couple circles. I'll dimension them after the fact. I know that this one here is going to be 6.3 millimeters. Again, that's based on the fact that I did a test print and I know how big this needs to be in order to print, so I'm going to say 6.3 millimeters. Another thing that I like to do is turn these inside edges to construction. So I'm going to say construction for that, and if there's any inside, we're going to say construction there. And the reason for that is when we select this geometry, we want to be able to just select this and get the entire, just the full circle there without grabbing all that other stuff. So you might want to go in and just make some of those other projected lines construction. When we're thinking about the flight controller mount itself, we want to give a little bit of a buffer because these are actually rubber spacers, and when you tighten the board down, they tend to swell a little bit. We want a support structure in place so that they don't swell too much, but we don't want to just exactly match that size. Things in CAD tend to be very precise, but when you get to the real world, you'll find that these spacers might be a little bit bigger, a little bit smaller. The print might be a little bigger or smaller. We obviously know that the print itself needs to be just slightly larger. So what I'm going to do is I'm going to dimension these, and if I give it a 5 millimeter dimension, you can see that gives me a little bit of a buffer there. Now at this point, we need to think about constraints and constraining all these elements together. If I add another dimension here and click on this 5, that'll link them together. You can also use the equal constraint. It kind of depends on how you like to work. Now, if I'm adding dimensions, oftentimes I'll link dimensions together simply because it's just quicker if the dimension tool is already active to click on another element and click back to that first dimension rather than hitting escape to get off the dimension tool, selecting the equal constraint and selecting everything. It's just a little bit more efficient in the overall process of the design. And depending on what the end goal of your part is, whether or not you have 2 dimensions or 1 dimension and 1 constraint, it's not going to affect the performance of the design drastically. So now we've got sort of our grounding points on the design. Everything here, again, is going to be patterned around. It could be circular or rectangular because this is a square. It really doesn't matter how we do that. But in this case, it's important to note that we're building everything from sort of the midline here and the midline here because everything's going to be patterned around. The way that I like to think about my designs initially is I like to just start with lines from the center points and just see what that looks like. Now, if I'm happy with that shape, then likely I'll just continue on with that shape. Now, in this case, I don't want to go center to center. If we look back at the other chassis that was drawn, you'll notice that there was this sort of horizontal section. Now, it looks like I'm on perspective only. There was this horizontal section where I came out from the mid and then I went up, and this is not the center point here, but you can see that I came out straight and went up and left this bump here. Now, part of the reason for that is to minimize material. You really don't need a ton of material. We're not talking about a ton of thrust or force from these motors, and you're really not talking about a huge overall mass. So the forces in the chassis are not really very high to the point where we need to worry about all of the extra pieces. So some of the initial chassis that I played with, I've designed probably dozens of these at this point, but some of the initial ones I've done straight lines. I've also done straight lines between the props and built a square. But again, we want to minimize material. We want to be as efficient as possible. So I'm going to take these lines and I'm going to delete them. And I'm going to start with sort of the same structure. I'm going to come out horizontally, and then I'm going to come up to that outside cylinder. This one will be vertical, come up to the cylinder. And then for me, I'm going to go center to center here. And then I'm going to draw center and perpendicular to the midpoint of that line. Now, I don't want to use this line, so I'm going to hit X to make it construction and X to make that one construction. Now, I'm going to use some constraints. I'm going to make this line and this line equal, and then hit escape. Now, the reason for that is because I want things to update and adjust very nicely. Now, we still have an issue in that these points are not the same. Now, you might be thinking to yourself, we have this line. We could simply just mirror whatever we draw here across this line, and that is perfectly valid. That doesn't always work. In this case, it does because we're dealing with a square, but it doesn't always work out quite that nicely. So one way that we can go around this is by using additional constraints or by using additional dimensions or construction geometry. Mistake. Or by using additional construction geometry. So what I'm going to do is I want to select this point here and this point, right click and say OK. That's going to essentially be escaping off the line tool. Now, if I make this line perpendicular to this line and I hit escape, I'm going to go ahead and make that construction as well. Now, these are going to move the same. And really all I have to do to fully define this is tell it how long I want this line to be and what angle I want these to be at. So I'm going to give this an 8mm dimension. And then let's go ahead and give an angle here. Let's say 20 degrees. That looks probably a bit too wide. Let's say 22. I think that looks pretty good. Now, the other thing that we need to think about again is connecting this to make some sort of solid structure. So I'm going to escape to get off my dimension tool. And I really don't want to build underneath the board. The board is supported by these spacers. It doesn't need any material underneath it except for where the screw is going to be. So really what we could do is we could build out as far as we want, as long as we have material connecting these. So this is a relatively small amount of material here. And another thing that we need to think about is this is the inside wall of the area where our spacer is going to be. So we actually are going to add additional circles, and I'll add another one down here. And these are going to have whatever overall wall thickness we're going to work with. So for me, I'm going to focus on 1mm. And in this case, let's go ahead and use the equal constraint just to show the difference. So I had to get off the dimension tool, select the constraint tool, and then select both of those. Now, if you have been using Fusion for a while, you might have also noticed that the right-click menu, if you make a selection, will list any constraints that can be applied here. So two circles we can have equal. They could theoretically be tangent to each other if their centers weren't already fixed. We could fix, unfix them, basically lock them down without giving them a dimension. And again, if their centers weren't already fixed, we could make them concentric. So that right-click menu is pretty handy, especially noting that it's contextual. So two lines, we could do collinear, parallel, perpendicular, equal, fix, unfix, and so on. So that is a slightly quicker way to get to your constraints, but it still, for me, takes a little bit more time than just making an equal dimension. Also keep in mind, if you use tools like offset, you can add an offset dimension, but each time you select additional geometry, it will add that additional dimension, and those will not be linked together. You'll have to go back and manually link them or delete them and make things equal. So again, it's just a matter of efficiency. Not that one way is right or wrong, but I find that using the linked dimensions is quite a bit quicker, especially as you're progressing through your design. So now that we have this additional thickness here, that adds a little bit more material here, and I can take a line and I'm going to go from sort of this inside section down to this one here. And once again, we're going to make this perpendicular. And really, as long as we stay outside of this portion of the board, we'll be fine. But I want to give it as much room as possible. So what I'm going to do is I'm going to figure out what this distance here between that point and this line is going to roughly be. So I'm going to use D on the keyboard for my dimension tool. And it looks like it's about 1mm. And I think that's going to be fine for us. So again, what we're really looking to do is we want to make sure that we build a chassis that is as light as possible. Now, if you find that this isn't enough material, this line doesn't have to go to the center of the screw boss. It could raise up, or we could determine a different angle here. So if we were to change the angle and shorten that line up, we could potentially get this just to angle all the way back into this piece. I think it's going to be fine for what we're doing. There will be more material underneath holding it together, potentially. So just keep that in mind that we're going to add things like a fillet in this corner, which will bridge this down. That can be a relatively large fillet. All of these different things that we can do. So now that we have this, we also need to think about the fact that our circle here is going to be the small diameter that's going to be around the motor. So we need to think about how much material we want around that. Now, in general, what we're looking at is a millimeter, which actually isn't very thick. You might potentially get deflection issues when you press the motor in to something that thin. For this example, I'm going to go ahead and stick with a millimeter. I'm going to link it to another dimension. And once again, this helps me because all I have to do is go back to this dimension. And let's say I want it to be 1.5. All those elements will increase together. And I don't have to worry about adding additional dimensions. One thing that we can also do is we can name this. So I can call this wall thickness and say equals 1. So now when I go into my modify and change parameters, I have this custom one that was called wall thickness. So you might notice that recently, the end of November, that Fusion updated. There are a couple things that changed. One of them is the parameter dialog box. All the same stuff is still here. However, you'll note that there's a filter for parameters, and now there's a plus user parameter at the top, where it used to just be a plus icon down here. Now you have to hit it here to add it. Still the same functionality, it just looks a little bit different. Now, in my opinion, this looks a little bit more like a Mac menu than it does a PC menu. I don't know if that has changed on the Mac side as well, but that's just my initial impression of that. All right, so now we've got quite a bit of a sketch here. We can start extruding this. Actually, you know what? Let's go back into that sketch. There's one more thing that I forgot to include. The last thing that I forgot to include is some sort of reference for the propeller. We don't necessarily need it right now, but sometimes it's good for us to have a reference in our sketch. So that's 32 millimeters. I'm going to turn that into construction because I don't really need it right now, but it is nice for us to at least have that there so we know what the extent of that is. And part of the reason is we're going to have to build some sort of propeller guard. It's not necessarily required, but if you're flying this thing around trying to go through gates or happen to bump into the wall, you do want some protection. Now, in the last design I did, I actually had these little ears that came up, and they printed relatively well, but I found out that if you bumped into anything, all it really did was it pushed these into the propeller. So in theory, it worked, but it didn't have quite the effect that I was hoping. So what we're going to do, instead of creating this entire outside profile, we are going to create somewhat of a semicircle. So this upper right-hand quadrant really only needs to go from the vertical position and down 90 degrees, because if we hit anything on the right side, then the prop guard around the bottom right one is going to also contact. So really, we don't need more than 90 or potentially 100 degrees, an extra 5 degrees in each direction. And it doesn't actually have to be the complete arc profile. We could put a point here, maybe one in the middle and one out here. So these are all things that we want to think about. We're not quite there yet, but again, it's just good to have that reference. So now that we have this geometry, I'm going to start to extrude it. I'm going to pick the areas that I want to extrude and make sure that we grab all these little segments. And in this case, remember, we're going to leave a little bit more of a gap around here, but I am going to include the centers for right now. And then I'm just going to pull this down. And what I want to do is I'm not going to be cutting. This is going to be a new body inside of our component. In this case, actually, we should have probably created a new component to start, but I'm not going to worry too much about that since we're focusing on the design. But what I want to do is I like to use the intersect tool because this gives me sort of a visual reference about where things are. I can kind of see what objects I'm overlapping. So in this case, we're overlapping those spacers and the motor, and we can determine whether or not we want to keep those. Another thing that we can do is to go to an object. In this case, we'll select the bottom of that spacer, and then we'll add an additional offset. Now, our wall thickness is going to be 1 millimeter, but I don't want the bottom of this to just be 1 millimeter. I'm going to have a little bit more since I do need some engagement with the screws. So I'm going to add 1.5, and then we're going to change it from intersect to new body. Now, the reason I want to do new body and not new component is because if I create a new component now, that sketch is going to still be at the very top level. So what I want to do is I'm going to roll this back before that sketch. I'm going to create a new component, call this chassis, It's very easy to forget this step whenever you're sort of creating your models. And then I'm going to expand this and roll to the end of my timeline. And you can see there's a bunch of other stuff in this timeline. Not too worried about that. So what we can do is we can note that our sketch is going to live at the top level of the design. We can activate our new component and then carry on with the extrude from there. And make sure that we grab all of those areas once more. Once again, we're going to do a solid center section because we're going to come back and add the holes and the other features later. And I want this to go down to the bottom of my spacers. We're going to offset it 1.5 millimeters. And now that we're inside of the component, the new body aspect is going to be automatic and it's going to live inside of this chassis. Now what this means is that I can't go back into the sketch inside of the chassis component. I always have to go back to the top level. Once again, it's not necessarily a deal breaker. It's not a huge problem, but it is something that you should be aware of. Now, before I get into adding the little lip on top of the motor, what we really want to think about at this stage is how we want to remove weight from this. So at this point, I'm going to right click on the chassis. I'm going to go to physical material and I'm going to give it an ABS material. Now you can give it whatever plastic material you want. Do it at the component level. That means any bodies we create inside of here will automatically inherit that material. And then we can take a look at the mass of the bodies individually if we need to. So this body right now is 1.8 grams. Remembering that it's only a quarter of the chassis, we still have a little bit to add and a little bit to remove. This means that this portion alone is going to be, 2 grams on each corner. So we're talking about, we're already at 8 and our target for the entire thing is 4. So we obviously need to remove some material here before we really get committed to the design. Now there are a couple of ways that we can think about this. Now if you want to just remove material where the propeller is and then allow your slicers to just do a very light infill on the rest, a lot of slicers will have options where you can determine the wall thickness. So we could go in to, in this case, the Creality slicer and say the infill wall thickness is going to be 1 millimeter, and then we could just let it do some sort of gyroid infill and reduce the mass that way. Now that just looks basically like you're flying a big block around, and while you might have the mass, actually down to a fairly low number, another thing that we need to think about is the airflow underneath the propeller. Now airflow is very important when we talk about these chassis. So the amount of material that we're using to support the motor right now is excessive. Like we have too much material here, and it's sort of an exercise, a challenge in engineering down to the right level. So we're going to leave this size here and we're going to talk about lightweighting. So the first thing that I want to do is I'm going to add some fillets. All of these corners on at least the outside portion, I'm not too worried about the inside just yet. All of these corners, I want to add some fillets. I'm going to begin dragging this out, and it looks like maybe about 2 millimeters would be okay. And the reason I want to do that is because I'm going to be using the offset face. I'm going to select this sketch. I'm going to offset the face. The inside portion, we really need to drop down. We need to extrude down a bit. So I'm going to show my initial sketch again. I'm going to say extrude. And now what we want to do is we want to take down these inside sections. And we're going to take them down to the bottom of those spacers. So if you just have the distance activated and you select something, what Fusion will do is it'll measure that. Now, if you want to actually maintain a parametric link, then what you should do is you should select that object. You'll notice that all the spacers are getting cut, and that's because there's really only one in the design and there are 4 instances of it. What we want to do is we want to select which object we want to cut, which is only going to be our chassis. So when we select our chassis, it's going to remove that material. However, there's another aspect of this that we should think about, and that's the fact that we want to remove more of that boss, and not enough of it is in this sketch. So this means we're going to need our own sketch to sort of work that out. To do that, I'm going to isolate the chassis. This is another good reason to use components. Very easy for us to isolate and start a new sketch. When we start a new sketch, we automatically will have the center points to add circles. So I can go ahead and add these 2. D for dimension, and we're going to add 5 millimeters here. And once again, it's quicker for me to just select the other one and hit enter. I could also project that from the original sketch. Either would be perfectly fine. Then I'm going to switch to my line tool, and I'm going to carry this line straight out. So it's going to be collinear, or parallel is going to be the one that it defaults to. And what we want to think about is also where we're going to be patterning this from. So I'm going to take sort of the vertical section at the top, the horizontal section here. I'm going to say coincident and select that and make those coincident. And this means that this line is going to extend until it hits that point. Now, this perpendicular relationship is likely problematic. I'm going to delete that and make sure that this is horizontal. And this one here is automatically vertical. So what this allows us to do is it allows us to extrude these sections, which will let us remove more material. All right, so we're going to take that and we're going to extrude that down into the part. And you can see that we're removing that material. Another thing that we could do, because we know that we offset from the bottom 1.5 millimeters, we could do that as a minus 1.5. And if we were driving these with parameters, we could link those together. So if we unisolate this for a second, if we were to take this design as it is right now, if we took this body and we did, let's say, a circular pattern about the origin. So if we were just to pick the y-axis right now, and we made, go ahead and select the y-axis, there we go. We should see that where we made those cuts will perfectly intersect with the rest of the chassis. And that's what we're looking for. We're looking for the ability to make that happen as we sort of pattern this around. We're not to that pattern stage yet. It's just every once in a while, it's good for us to sort of check. So once again, let's isolate the chassis, and we're going to start to get into creating some pretty intricate work inside here. So it's a good idea to do a quick save and make sure you don't lose anything. So let's go ahead and start a sketch and use this top face here. And then we're going to use the offset tool. So we're going to take the entire outside chassis and we're going to do minus 1 millimeter or minus wall thickness. Because remember, we used that 1 millimeter value before, so it's already in our parameters. And this right here is also going to allow us to sort of fill in the gap here. We can do this with either a circle or an arc. If we grab the arc, we want to make sure that we grab before the fillet. And now we've got this sort of inside section that's 1 millimeter offset from everything. Now, this can produce some problems in these corners because it's relatively tight. And what you might find is that maybe you want to manually sort of section off the corners and leave them solid. That is a potential option. You don't necessarily have to do it, but sometimes it might be helpful to sort of break this, break this area up. It is important, however, to think about what we're doing here with the tools. We're going to be creating a split. And when we create a split, what that means is that this section here is not going to work. The split tool doesn't like it when two edges overlap. It wants them to end at the same point. So it's not going to let us split this geometry nice and clean. A way that we can get around that is by trimming these. And if you've used this before in Fusion, you'll know that as soon as you trim this, it's going to flip out because it doesn't know where those references went to. So this means that we're going to have to fix them by doing things like making these two concentric, and that'll fix that problem. And then when we trim this section here, you can see that it tries really hard to fix those constraints. It does give us some errors, but it does try to fix those. We're going to make that construction so we don't have to worry about it. This one here can be construction as well. And what we're looking for is when we double click this, whatever is selected here for that entire profile, that's going to be used for our split. So in this case, I'm going to get rid of these lines because I don't want to do a bunch of additional trimming. Obviously, if your goal here is to make a chassis, you're going to have your own ideas about what you want it to look like. But just keep in mind that when you do a sketch like this and you try to trim things back, you'll likely have to go back and fix some of those constraints. All right, so now that we have this, we're going to use split body. The body to split, the tool, once again, it's going to grab that entire profile. And now what we have is we've got our main body and sort of this center section. The reason that we're doing this is because the main body is going to be essentially our structure. The center section, what we're going to do is we're going to hack this apart to have whatever sort of structure we want to include for our light weighting. Now, in the other chassis I showed you, I did this hexagonal pattern, and you can see it just, sometimes it kind of leaves these little areas here. You can see that I sort of omitted areas in the corners. Obviously, these chassis are not identical. They are slightly different. You can see that I have more material in this corner than we have. So there are definite differences between the chassis. But having said that, that's sort of the point. This is a design exercise. So what we're going to do is we're going to sketch on the top face, and we are going to create our hexagonal pattern. Now, this unfortunately is not the easiest process to do, and you need to think about where you want to start. So what I'm going to do is I'm going to create some reference lines right here at the middle, and I'm going to make that construction. And then I'm going to go to my polygon tool, and I'm going to use the inscribed polygon and start here right at the midpoint, and then create something. All right, we need to determine the orientation of it, and we need to create a second version of it. And these are going to have to be equal. We need to figure out what size they're going to be. And for me, I'm going to go from here to here and say 2 millimeters. And I'm going to do the same thing over here and make those equal. And then I want to make sure that these edges are vertical. I'm going to escape, and then I need to position this one where I want it. Now the trick to this, at least for me, is once again to use my line tool. I'm going to go midpoint to midpoint, hit escape, make that construction, and then I'm going to make this perpendicular. Now when I make this perpendicular to each of these references, the only thing that now I need to control is the distance. Those two endpoints are going to line up, and all I really need to worry about is how far apart these are going to be. Now in general, this would be our wall thickness, but I want to minimize the mass here, so I'm going to divide that by 2 and leave 0.5 millimeter. Now this is actually pretty important because your printer might not be able to print that. You need to do some testing to figure out if it can print 0.5 millimeter. If we take a look at this other chassis, this printed just fine, and this one is 0.5 millimeter. If I went smaller than that, it had problems. If I try to do 0.4, which is the nozzle width, or if I went even smaller, it was not able to handle it in the slicer. So I found, at least on my printer, that 0.5 millimeter seems to work okay. Now we want to take a look at creating our pattern. Now, this is going to be a rectangular pattern. I'm going to double click each of these and then start to drag it out. Now I want to do a spacing amount, not an extent amount. And remember, we're 2 millimeters wide and we want 0.5 millimeter between. So we're going to do 2.5 in the width. Now the vertical one is a little bit different. As I start to drag this up, we need to find that balance where we hit the correct amount. Now, when we take a look at this, again, it's spacing, and you can see that it's minus 4.3. Now, this is not going to be a nice round number like the 2 millimeter width, so this is probably going to be close enough for what we're doing. If you want to get really specific, you can put a driven dimension from these endpoints here and figure out what that height is and where you want this to be. I'm not going to get into that for this example, but I am going to, let's go ahead and drive this. This is going to be symmetric. Because we are starting in the middle, I want to make sure that we drive it in both directions. And then we're going to increase the quantity until we cover our entire part, or at least the area of our part that we want. All right, so that looks like it covers pretty much everything. The corners I'm not too worried about. We're going to leave extra material there, and I'm going to say okay for the pattern. The last sort of trick of this is going to be to just create a box around the outside. And then we also want to double click our parameter here, or our profile here, and hit X to convert it. Now the reason we want to do that is because now what we're extruding is this sort of center section here. So when we finish this and we click extrude, we have one selection. We drag this down through our part, and we're going to use the intersect option. So what this is going to leave us with is only the material where we intersect. And you can see that there are some little pieces that get sort of left behind. That little piece I'm going to remove. I don't need it. But then when I bring back my main chassis, we can combine these together, and now we've got this sort of structure inside. Another thing that we can consider is that we're printing this thing from the bottom up. So I can use tools like press pull, which is Q on the keyboard, And I can drag this down a little bit, which will still give me some of the structural benefit. I'm still printing from the flat bottom, but now I don't need the extra material. And you can determine how much that saves by measuring the chassis. So we're going to go to our properties. We're going to take a look at physical. You can see right now the mass is 0.902 grams. If I go back before this and take a look at the properties, we should see what the difference is and whether or not it's worth it. So it was 0.902 and now it's 0.99. So almost 0.1. We're really not talking about that much mass, but it is a little bit, and it is over a quarter of the design. So let's go ahead and combine these two together, joining them, and now we have sort of this unified geometry. This corner is likely going to be problematic if we try to fillet it, so I'm going to add one fillet first, and then I'm going to fillet again, and I'm going to add another one to sort of fill that in. If we try to do both at the same time, it will not be happy. I can promise you that. And then we'll do the same thing at the bottom. We'll do one, okay, and we'll repeat it. And we'll take this one and just sort of drag it in. And that looks okay. So once again, let's go ahead and save, make sure that we don't lose anything. And it looks like, again, I want to make sure that we're in the top view. And then everything looks pretty good from here. Okay, so the next thing that we need to do is we're going to add the little cap for the motor. So we're going to create a sketch. And I'm going to do a circle that matches this diameter. And then once again, we don't want to print this too far in. We just need a tiny little stop. So I'm going to do 5.5 millimeters. And we're going to extrude this up just, let's say, 0.5 millimeter. And that could be maybe wall thickness divided by 2 again, so to try to sort of keep with all of those values. And then once again, this prints okay on my machine, but you might find that adding a small chamfer here could potentially help. And another thing, if you happen to run into a situation where you've got things like these tiny little areas here, you can select these inside faces. So for example, these two faces, and hit delete on the keyboard. Fusion's pretty good about patching that geometry. Now, you don't necessarily have to get rid of those, but that small geometry really doesn't print very well. And so like that little pocket there might not work. I'm gonna hold down the left mouse button, select that inside face and hit delete. And you can see that it opens it up. If we instead select the other faces, so all 3 here, and hit delete, it'll be able to fill that in. So the selection does matter, but if you have any of those little areas, sometimes it's nice to just clean that up. Makes the printer job just a little bit easier. Okay, so at this stage, we need to also think about the mounting holes for the controller. All right, so in this case, if you happen to buy the kit comes with some relatively tiny sort of self-tapping screws, really small, not a whole size that you could print, something that you would definitely have to drill. Now, I found that those screws allowed a little bit of flexibility in where you could put things, but you weren't able to screw the camera down using that. You would need another big piece that would have to attach somewhere to put the camera. Now, what I found worked well was to create a little bridge piece and use larger machine screws. So again, you kind of have to make that decision. I find that it was easier to print the holes and then drill them out to an appropriate size, so that way you don't have to worry about how accurate the printer is. So what I'm going to do is create a sketch. I'm going to do a circle, and in this case, I'm going to go ahead and just do 1.5 millimeters. And that'll give me something that's big enough that I can print out later. So I'm going to project that, and I'm going to do another hole here. And for this one, because I'm not on the dimension tool anymore, I'll just make those two equal. I could also use the hole tool very easily because it'll allow me to find the center points. But in order to use it for multiple locations, typically you have to have, you have to have something else there. You need to have a sketch with points there. So we're going to cut those through the chassis. And now we've got those holes. Before I pattern this, I do want to add some fillets in here just to give this a little bit more structure. We want to make sure that we're not obstructing the connectors, so that's important. We need to be able to plug the motors in there. So let's go ahead and make this 2 mm, and that'll give us enough material. And this little section here, I think I want to get rid of that. So I'm going to select these inside faces, hit delete, and allow it to patch it. So once again, those small openings, those are going to be harder to print. So if you can get rid of them, probably just a good idea. All right, so now we have a quarter of our chassis. We can pattern this. And again, because it is a square, you could use rectangular. You could mirror over the, in this case, the XY plane and then the YZ plane, or you could do a circular pattern of the body. Now, the circular pattern seems like the easiest option to me. If you are making a tri-rotor a tri-rotor drone or something like that, then obviously circular pattern is pretty much the only option. But we can go ahead and just combine all these together. And now we have a chassis, or at least most of a chassis. It's a good time for us to check the properties, see how close we are to that 4 grams that is sort of my ideal. And we're at 3.435. So that is pretty darn good in order to keep the weight down. Now, if you have a keen eye and you're looking at this and maybe you've had a couple drones before, you might think to yourself, if they don't have that much force, why do we even need this sort of honeycomb section in the middle? You probably don't, honestly. You could probably get away with printing the outside and maybe having just one support rib in there. I think it looks pretty cool. It doesn't add that much weight, but ultimately you have to decide for yourself what your design is going to be. So as I mentioned early on, we are not going to go through the entire process of creating a sort of a ready-to-go drone chassis for the competition. I think that the heart of the competition is that you make your own design. There is still one element of this that I do want to tackle, something that we haven't done yet, and that is the guard for the propeller. So we are going to tackle that part. We're not going to get into sort of the battery holder area, which in my chassis here, that also doubled as landing gear. So it was the lowest point below the motors, and that allowed me to sort of rest the entire drone on this. If it's not sitting level when you try to take off, because it has some automatic leveling characteristics, some of the props will spin because it's trying to auto level itself. So you do want to make sure that you have some sort of landing gear, whether it attaches to the motors or in this case, I used the sort of battery holder as that. But again, we're not going to approach that. We're going to be talking about creating our prop guards. Now, when I look at this, the props are relatively high, but again, we're not going to be building up all the way around them. I want to really reduce the amount of support I need, and at this point, there are no supports needed. So what I'm going to do is I'm going to start a sketch on the bottom, and then I'm going to build out that prop guard. However, since we are patterning everything, the best approach is to go back before you pattern this body and build out the geometry and then just, roll past that body. So when we take a look at this, once again, we're really looking at a couple of things. We're looking at bumps from this position here and bumps from this position here. Now those two positions are essentially going to be where you would hit something. You could potentially hit it on the corner. So something at, let's say, 45 degrees would also be beneficial. Now, a couple of things that we need to sort of concern ourselves with or think about here. One is going to be airflow. We already are restricting airflow by having the chassis here. Now, this is a decent amount of restriction. Now, in reality, we might want to sort of shrink that down. And everything is parametric with the exception of these delete faces. The second we added these delete faces, that direct editing is going to break any chance that we have of updating this easily. We'll talk about that in a second, but most of the things here that we did are going to be relatively parametric. So we can edit the design as needed. I'm going to project that sketch, or at least that circle, into our design. I'm going to snap these to that. And then I'm going to create another circle and dimension this at our wall thickness. So once again, that 1 mm. What we're doing here is we're going to add just a small guard that's outside, but we need to connect it with something. And connecting it with something means that, again, we have these prop obstructions. So what we're going to do is use the line tool again. I'm going to extend a small line out here. I'm going to extend one here, and I'm going to extend one here. We can use the same honeycomb structure to build out, or we can just carry out a thin little section and connect these out. Now, the way you decide to do it is really up to you. You can offset these in either direction. I'm going to offset that. I'm going to make sure that I use wall thickness. I'm going to repeat that down here. I'm going to use minus wall thickness because I want it to go down. And then in the one here, I'm going to use wall thickness divided by 2. And repeat that, and it's going to be minus wall thickness divided by 2. And the reason I'm doing that in the middle is because I don't want it to be offset. I want it to be symmetric. So now what we have is we've got these areas that we can print or we can include in our extrude, and those will support the prop guard without really adding much obstruction. Again, you can go back and you can add some honeycomb in, but really all you're doing is you're sort of adding some obstruction to it. So with that in mind, what we're going to do is we're just going to extrude. I keep saying print. We're going to take this little section, and we're not going to take it all the way up, but we're going to add just enough that we've got enough support here. So 2 millimeters is, let's do minus wall thickness times 2. And again, we're keeping all these parameters linked together. So then we're going to just add some fillets because if this thing bumps into anything, we want to give it the best chance of surviving. These fillets can be whatever size you want. I'm going to add fillets to the outside, and these are going to be the additional thickness of it. So we had 1 millimeter, so 1.5 on the inside, 2.5 on the outside. And I also need to do that where it connects to the chassis. So I'm going to just hold down Control or Command if you're on a Mac. I'm not too worried about the outside one being larger here because it's not like a consistent wall thickness thing. But that gives us a little sort of bump there. Now we could get rid of this middle piece here and this would give a little bit of a spring. And if we want to do that, then we should consider maybe potentially making this a larger diameter, because these things will flex a little bit, and then if it's going to hit the prop anyways, it's not really doing you any good. So now, because it's part of the body, we can pattern it, and you can see that it sort of comes out there. We can double check our bounding box, make sure that we're still within the bounding box, and it looks like we just are. We could go just a little bit bigger to protect those props, but that does give us a couple of millimeters. We were already about 1 millimeter outside, plus another, so we've got 2 millimeters there. And that means that if we hit a wall on this side, it'll protect the props. There is a chance that you could intersect with something here, and if you want to carry that all the way back in, you certainly can. But again, the name of the game here is going to be minimizing the mass. So let's take a look at our properties and see how much that added to the overall weight. So when we take a look at this 3.981, we're still under that 4 grams. That was sort of the initial goal. So again, adding more around would potentially add enough weight to get us over that 4 grams. You could remove that middle piece, potentially make the middle one a little bit thinner so it does flex a little bit. All of these could affect the overall design. So at this point, we have everything we need for the main chassis. The main chassis is done. We don't have a battery holder. We don't have the camera holder. And again, if you're running a camera, you need to run 2 batteries or you need to sort of find a way to power them both off of the same connector. You're not going to get a ton of flight time out of these things, so running the camera and the drone off of 1 battery is probably not ideal. It kind of just depends on what your situation is. At this point, if you want to see more, if you like this, I can carry on doing a few more of these. If you want to see me print this and you want to see some video of it flying, let me know. I haven't printed this chassis. Obviously, we just drew it, so it's brand new. But I can certainly print it and assemble it and see how it flies and see where we can make some design decisions. If you happen to tackle this through the Airgineers competition, or if you decide that you want to just make your own drone, you have any questions, please let me know. I'm by no means a drone expert. I have designed and built a few of these things, micro drones and full-size drones. So I do have a little bit of experience. Maybe I can help answer some design questions. This is a pretty fun one because it's an indoor drone. It's something that you can fly inside, so you don't need to worry about getting the drone registered or having your license to fly outside. If you do happen to get into the larger drones, there are some additional criteria, things like registering your drone, which is a little bit interesting if you're designing your own chassis and you're printing multiples, how that's going to work. You will need to have a license. I think everywhere in the world. I'm in the U.S., so our restrictions might be slightly different, but we have restrictions about how high they can fly, how close to an airport. I think it's within 5 miles you can't fly, up to 400 feet or so. Line of sight needs to be maintained. Even if you have FPV goggles, you still can only fly about a mile away from your position. So there are all these different things that you need to worry about when you're talking about the bigger drones that are obviously much faster. This is different because you can fly it inside your house. You don't need that much room to fly it. They are really quick and agile. The flight controller does have auto stabilization on it, so it can sort of self-level, but you can also turn that off and you can actually get them to do rolls and flips, and it can be very, very acrobatic. Now, if you do design something for that, I would suggest caging the top of the propellers. If you land it on carpet or if you land near anything, then you can very, very easily catch them on something, and it might try to auto level itself, and they'll just be spinning. So fully protecting it is going to be important, but keep in mind that it's all a matter of the mass. So that is problematic. That's something that you need to deal with. So once again, if you have any questions on this, anything that we covered here, please let me know. If you want to see me print this thing, assemble it, and fly it, let me know that as well. I'm happy to go ahead and print it and do that, but at this point, we're already over an hour in on this video. I don't want to just carry it on for another hour. So if you do want to see that, let me know. And as always, if you have any questions, you can always email me, support@caducator.com. If you want to be a part of the Discord server, you can email me and I'll send you a link to that. But as always, thanks for watching, and we'll see you in the next one.